Okay, now I think what we should do is just revise something from grade 11 to do with energy in reactions, but endothermic and exothermic reactions.
Yeah.
Important stuff.
Now, endothermic and exothermic chemical reactions is something that we dealt with thoroughly in grade 11, and we now want to revise it quickly because it is crucial for you to understand it more when you're dealing with chemical change in grade 12.
All right, let's take a look at this first slide. Now, what we're plotting here, this is not time. Okay, this is just the reaction as it proceeds. You see, we're talking about reaction proceeding. We are not measuring time on the x-axis there. So don't believe that that tells us how this reaction is proceeding. All we're doing is we're looking at the relationship between the energy of the reactants and the energy of the products. And what we plot on this y-axis is this thing which we will call chemical potential energy. That is the potential that a chemical species has for reacting. Now here we've got the reactants. This is the combined energy, if you like, or the average energy of your reacting molecules. Now, in order for them to undergo a successful collision, they have to have enough energy. Now, having enough energy might mean that the temperature has got to be right so that they're moving fast enough. It might also mean that they've got to be enough in the correct orientation, and so molecules like that can't react when they're like that because they must be in that sort of orientation. And all of these things together added up give us something called the activation energy, which simply is the amount of energy required in order for successful reactions to take place. Now, the successful reactions take place, and we find in this case that our products, the average energy of the products, is below that of the reactants. In other words, the heat or energy of the products, HF, minus HI, which gives us delta H, there, is equal to the final energy minus the initial energy. If the products, the final, are less than the initial, then this term will be less than 0. Now, what has happened here is that during the reaction, in going from the reactants to the products, energy has been lost. In other words, the products having less energy than the reactants means that some energy must have gone out into the environment. It must have been, it's never destroyed, but it could be lost to this particular chemical reaction. That means heat is evolved during the reaction. That means if this reaction happens in a container which you're holding in your hand, you will feel it getting warmer. This is called an exothermic reaction, and it's a little bit odd to see delta H being less than 0 when heat is evolved, but here you can see the reason for it. Okay, I've said enough. It's your turn now. Tell us about endothermic reactions.
Yeah, just like Peter said, it is always very confusing, more especially for people still learning these things, to understand that you holding something, a container where a reaction is taking place, and you're feeling it is getting hot, but you're saying it is giving energy out of it
and
into
that
the
delta H is less than 0.
And delta H is less than 0, yet you can feel the energy coming out in the form of heat. Now let's just then look at the opposite of that, which is endothermic reaction. Let's see what happens there. Now you can see immediately now that there is a change in the form of the graph that we saw earlier in this one. For this one, the energy of the product is at a higher state than the energy of the reactants. Now, this means that during the process of the reaction, the reactants or the chemicals there have gained some energy. And that gained energy is shown to you there by the blue arrow. And that is our delta H, our change in the heat of reaction. Now, because this energy has been gained by the molecules, it means that our value of delta H will be positive, which means that the energy of the change in energy between that of the products and the reactants is such that it has increased. So HF, energy at the final stage, greater than HI, energy at the initial state. So we see that the value of delta H for an endothermic reaction is positive. Now we want to leave you with an activity now, and we are going to discuss this activity with you in the next lesson. The activity is to explain the following. Why, when a chemical reaction is endothermic, it feels cool or cold when you touch the container in which the reaction is taking place. Or at the same time, you can also be looking at a situation where if it is an exothermic reaction, when you touch the chemical, the container in which the chemical reaction is taking place, you feel it is hot. Why? Try and explain or give reasons why you feel like that, and we'll discuss this in our next lesson. Right, and that marks the end of our lesson for now, and see you in the next one.
See you in lesson 23.
Summary. In this lesson you learned what is meant by reaction rate, the factors which affect the rate of chemical reactions, to explain in terms of collision theory how the various factors affect the rate of chemical reactions, to suggest suitable experimental techniques for measuring the rate of a given reaction, to define activation energy, how to use a graph to show the distribution of molecular energies to explain why only some molecules have enough energy to react, how to explain, in simple terms, how some catalysts function by reacting with the reactants in such a way that the reaction follows an alternative path of lower activation energy.
Learning Channel offers an extensive educational collection ranging from grades 8 to 12 in alignment with the National Curriculum Statement. We offer DVD and workbook sets in a number of different subjects. To buy the Learning Channel series, check out our website on www.learn.co.za or call us on 011 639 0179.